Welcome to my playlist about beta decay. Let's start by introducing what my goal is in this particular video series. I was doing the In Search of a Quark, and once I got to this point, I felt I needed to break stuff up and get a way to get into the math properly. So, here we go. My name is Enrico Fermi. No, it isn't. My name's Larry Wells. But let's imagine that I'm Enrico Fermi and I just read this paper by Wolfgang Pauli that predicted a new particle that gave that occurs when we have beta decay. Beta decay, the most common one is carbon 14. I've done some videos about carbon 14 and how it decays into stable nitrogen. But anyway, let's talk about what's going on. And I'm going to come up with a theory, and the theory is going to use various kinds of different math, and it's going to involve quantum mechanics. So this first set of videos is going to just show what the preparation is to understand the paper written by Enrico Fermi in 1934. 1934. Wow, that was quite a while ago. That was what, 70, 80 years ago? I don't know. That's quite a maybe 90 years ago. My first job is to talk about how we detect the decay, which is really an electron shooting out of there, and why there's a suggestion that there's another particle that's also ejected. We have to look at the energy spectrum and look at it two ways. One is, if it's just an electron, what would the spectrum look like? And if the spectrum doesn't look like that, what would fill in the gap so that the spectrum is supposed to be that way? And that's really the first step that Wolfgang Pauli was fighting with. So let's look at some pictures of spectrum and try to see what my point is on this. Let's look this over. Got intensity. That means how many uh, particles are in this particular range. So here we show a highest number here and a lowest number there. Now, what's this all about? Well, we show that this is the energy of an electron. So the energy of the electron is zero point 0.4 and the units are mega electron volts. So if it was just the electron, then that would be the energy right here, and you'd have a spike and it'd go right down there, right down there. But instead, we extend way out here to this 1.16. Now, what's the deal with that? Well, the remaining energy is taken up by the neutrino. So the 0.4, and you subtract that from the 1.6, then you get a 0.76 neutrino energy. I hope that helps you understand this stuff a little bit. This picture shows a nucleus and an electron escaping, which is the beta decay. And down here we have a little bit larger thing where we have a neutron as producing three different artifacts. One is a proton, one is an electron, which means that this has to have a positive charge, and an anti-neutrino down here. The bar over the top indicates the anti-neutrino. Here's what's called a Feynman diagram. And if you have watched any of the quark videos, you notice that I've got a proton and an up, a down, and an up quark here, which stands for the proton. And in like manner, I have an up, down, and down uh, quark here for the neutron. This ends up being a neutral charge. This ends up being a positive charge. Notice that the arrows are going in this direction. And you notice that these quarks here, the up and the down, their arrows don't have any big difference there because there's no interaction here. But now we're taking a down quark and changing it into an up quark. And when this happens, it releases a, remember on some of those energies we released a photon? Well, this is a weak force boson. It's really get funny little names here. But anyway, that weak force boson then is going to result in a anti-neutrino and a electron. Now notice this arrow is going down mainly because it's an anti-neutrino. One last look at this picture. The fact that this is a continuous spectrum said that there had to be more energy than just the energy of the electron. Whatever particle created this extra energy, it had to be from some other particle, which became called a electron neutrino or just a neutrino from the Italian word which means small, so it's like a small neutron. Okay, I hope you absorbed that a little bit, but now I want to bring up three assumptions that Fermi had in his report, which is what we're trying to get ready for. One of the assumptions is that the number of electrons and neutrinos, or in this case, antineutrinos, are not necessarily constant. Now, let's look at the atom that we're talking about that's being decaying. It has pretty much a constant number of neutrons and protons. Not the same balance necessarily, but if you add up neutrons plus protons or the atomic mass, that pretty much stays the same during beta decay. But the number of electrons and neutrinos, that will vary depending on how the neutrons and protons are switching around. Second assumption is that the heavy particles, which are the neutrons and protons, are really one and the same value, and some of them have a property of 1, which is a neutron, and some of them have a property which is -1, which happens to be the proton. Third, Hamiltonian. Now, if you looked at some of our other quantum mechanic uh, problems that we've worked on, that were simpler problems like particle in a box and harmonic oscillator, we had to come up with the Hamiltonian. So when we'll have to do that here also. So when we come up with the Hamiltonian, we'll have to make sure that when we build this thing up, that every time there is a change in the proton and neutron balance, that we also have a corresponding change in creation or of a electron and an antineutrino. Next, we're going to really dive into this and talk about this idea of second quantization. This is going to be a real stretch for me, so it's also going to be a stretch for you as you look at this video. But the basis of Fermi's paper requires us to deal with this idea of second quantization.